Hello and welcome to the tutorial. Today I will try to demonstrate the computational capabilities of our program, Rawlplug EasyFix Pro, focusing on chemical anchors. We will make use of a multi-bay shop floor plan. This view clearly shows the hall's primary and secondary columns, which, according to the design plans, will be made of wide flange beams. The secondary columns will be made of type 220 and the primary ones of type 300 sections. The base plate is made of 20mm thick steel and its dimensions are 600 by 600mm. There are 2 rows of 3 anchors. The fasteners used are hammerset anchors, 30mm in diameter and 500mm in length. Our task is to replace the original anchors with bonded anchors, and this is where the EasyFix Pro programs come in handy. Let's start the program. It displays the start window with 2 tabs available. The Project tab contains icons for individual calculation modules. The other tab is Options. This is where you can enter data to be stored in the program memory and applied each time it is started. The first time the program starts, its language matches the operating system's language setting of the computer that you are using. You can obviously change the language by selecting it from a drop-down list. The same applies to the print language. It is not obligatory, and the print language and the interface language are the same. For example, you may well perform calculations in English and print results in French. The section below allows you to define units to be used by the program in calculations. Both metric and imperial units are available for dimensions as well as load. Here, you can change the factor which determines the distance between the anchor and the base plate. The default factor value is 1.5. The bottom screen section contains internet-related settings and buttons that enable program updating. Data entry sections and fields are found on the right-hand side of the screen. This is where you can enter the company name, address, or email. For instance, chosen name at rawlplug.com. In order to store all the data in the program memory and enable it to use them each time it starts, they must be saved. You can do that using the Save icon. Clicking it makes the program save all the data entered and apply the settings each time you run it. You can now navigate back to the Project tab and click the base plate icon to enter the module for anchor parameter calculations according to the ETAG 001 method. The program window consists of 4 sections. The top section contains system icons. Starting from the left, the icons are used to create a new project, open an existing project previously saved, save a project, save a project under a different name, print, undo the last action, redo it, retrieve information about the program, and display the help window. Below the icon bar is the data entry section with 4 tabs: fixture, anchors, substrate, loads. The middle section of the screen shows a 3D model for the object of calculations. You can rotate the model to view it at any chosen angle for better clarity. It also may be viewed in planes corresponding to individual axes. It is easy to return to the previous view, Just click the refresh button and the program will display the original model view. The right-hand side of the screen holds the results section with 3 tabs. The first one is Results. Project details include data partially extracted from the Options tab. The last tab is a technical repository where you can download documents such as .dwg drawings or approvals. Back to our project. Let's start by entering fixture data. You can choose between steel and wood to set the fixture material. We select steel. For the fixture shape, there are several basic shapes to choose from. This time, we should select a rectangular shape, or a square to be more precise. Let's enter the dimensions, 600 mm. They are automatically applied in the model. You can also enter these data items directly in the model. Just click a dimension line and key in the value of 600. Our model has slightly outgrown the display space, but in order to scale it down to the right size, just click the refresh button and the entire drawing will fit into the screen. We still haven't declared the fixture thickness. Let's enter 20 mm. You can also optimize the fixture thickness, but this can only be done after all the section, load and anchor data have been entered. Moving to the rolled section part, let's choose the section type, i.e. HEA, from the drop-down list. And then the dimension of 300 from another list. You can also rotate the chosen section against the base plate by entering the angle value. It will be rotated automatically. In this case, the section is positioned perpendicular to the base plate edge, hence the value of 0. You may decide to apply asymmetric placement. Checking this box and entering the relevant data, e.g. 50 and 70 mm, will move the section accordingly against the base plate center. Since we are dealing with a symmetric layout and the section is positioned in the base plate center, let's uncheck this option. Another set of options to choose from is available in the lever arm section. The program's default value is none. However, you may also choose to apply the without clamping option with full restraint or without it. Another option is with clamping, again with and without restraint. And the last option is with grouting. Clicking the latter will display an additional section where you can set the grout's compressive strength and decide whether to fill the holes between the base plate and the anchors. It will compensate for the bending impact on the anchors when grouting. And, since there is no lever arm included in the case we analyse, let's click None. We can now navigate to the Anchors tab, where we will decide on the arrangement of anchors. Let's choose 2 rows of 3 anchors each. The program allows you to define any chosen number of anchors in n rows with rectangular layout, as well as any number of anchors in a circular layout. You can also apply symmetric or non-symmetric spacing. Where the latter is the case, you will need to enter all distances between adjacent anchors. In this case, we are dealing with 2 rows with 3 anchors in each, and it is one of the pre-defined layouts. After clicking the icon, the corresponding layout is applied in the computational model. It is obviously possible to move anchors against one another and against the base plate. The spacing between anchors in our case is 240 millimeters. The data may also be entered on the drawing after first marking appropriate dimension lines. The spacing between rows of anchors will be 460 millimeters. Another available option is to introduce elongated or bean-shaped holes along the chosen baseplate edges. This will prevent the given row of anchors from transferring shearing forces towards the edge. There are no edges in our case, so let's leave all anchors marked. You can also distribute anchors asymmetrically against the baseplate. For instance, introducing the values of 50 and 70 millimeters will cause anchors 4, 5 and 6 to be placed outside the baseplate edge. This will trigger a message to be displayed in notes. The layout we are dealing with is symmetric, therefore we disable this option. Since the number of models of standard anchors is limited under ETAG 001, Rawlplug has developed the Rawlplug Engineering Design Method, abbreviated to REDM, which makes it possible to perform direct calculations in any chosen layout of anchors. Checking this box will allow you to calculate non-standard layouts. Another item in this tab enables you to change the A factor value preset in the Options tab. Let's navigate to the Substrate tab now. This is where you can select the concrete class according to the classes subject to the European approval. We choose concrete class C25/30. It is also possible to define a custom concrete class by entering specific compressive strength corresponding to non-standard concretes. Coming back to our case, let's select concrete of class C25/30. You may choose between two concrete categories, either cracked or non-cracked. We select the non-cracked concrete. You can also define the type of reinforcement, ordinary or concentrated. However, the reinforcement is none in our case. We may select edge reinforcement options, either straight or with stirrups. And again, we choose none. We can now enter the baseplate thickness. The value we enter is 800 millimeters. You can also define individual edges. Clicking the edge icons will practically transform our baseplate structure into spot footing. The boxes allow you to enter values of distance between the edge of concrete and the nearest anchor rows. Let it be 300 millimeters. What we are dealing with is a slab. Therefore, there are no edges, and they have no effect on the load carrying capacity of anchors. Let's disable them all. Below, you can define the short and long-term temperature range. Let's choose 40/24 degrees centigrade for our case. The bottom section allows you to define installation parameters. The first one is the drilling method, either hammer drilling, diamond drilling, or drilling with automatic purge cleaning. Let's choose hammer drilling. The other option is installation conditions, i.e. dry or wet concrete, water-flooded holes, or contact with seawater. We are dealing with dry concrete here. The last data entry tab is Loads. It allows you to choose between design or characteristic loads. Having selected the characteristic action, you can enter custom safety factors for each load type, either permanent, variable, or accidental, making the program convert them into calculated values and sum them up. In the case we review, the design loads have already been calculated using a separate program for static calculations, so we only need to enter design values. Loads can also be defined directly on the model by marking appropriate force or moment vectors. For example, let's set the pulling force to 57 kilonewtons. This can also be done in the Loads tab. We define the shearing forces of Vx at 0.5 kilonewtons and Vy at 23 kilonewtons. The same applies to moments. You can enter the mx value of 76 kilonewton meters on the model. There is no torsional moment in this example. You can see that the program has already performed all the calculations, but before proceeding to the Results tab, let's return to the very beginning, to the Fixtures tab. As I have already mentioned, you can calculate the base plate thickness, and since we have entered all the required data, we can make use of this option. Having clicked the Calculate Thickness button, you can either choose to use the program data or the Use Defined data. Let's set the steel type to carbon steel. You can select the standard applicable to the steel and the steel grade in line with the chosen standard. You can also define the safety factor for the calculations. Clicking Calculate makes the program calculate the recommended base plate thickness, i.e. 31 mm. Since the thickness we originally assumed is 20 mm, you just need to click the Apply button to change this setting, and the program will automatically migrate this value to the computational model. It's time we switch to the Results tab. The top section of the Results tab contains the ETA Only box, checked by default. This means that the program uses data contained in ETA documents only. Unchecking this box will make it possible to use data from sources other than ETA documents. The program will start extracting data from the Rawlplug Advanced Design database containing data exceeding the framework of ETA appraisals. They are pieces of data which originate directly from approval tests, and so they include no rounding applied under ETAG or from Rawlplug's in-house tests. You can apply different filters to the results. Basic filters enable you to choose the anchor type, and we are dealing with bonded anchors here. You can also choose from the available resin groups, and our choice is any. The anchor rod material, and it is galvanized steel in our case. The thread type, either external or internal, and the size. Since the design assumed in the original design is M30, let's select it from the drop-down list. The resin recommended by the program is R-KER2, and the rod is M30, made of the 5.8 steel. The results have been confirmed. The combined load reaches the level of 87.2%. You can also optimize the parameters in a slightly different way, using the Optimization button. It will display a table containing data of all anchors meeting the conditions preset by the filters applied. You can narrow down the table entries to anchors with the utilization factor below 100%. It is also possible to filter the contents according to the utilization value or the embedment depth. Marking an individual anchor will trigger a change to the data displayed in the Results tab and the anchor type recommendation. In order to make the Results tab more visible, you can hide unused filters as well as the picture. Instead, you can expand another section. For instance, the forces acting on anchors. This displays a table containing values of loads affecting the anchors. Having displayed the drawing again, you can see numbers of individual anchors as well as the neutral axis. You may also display details of loads. With bonded anchors, it is possible to manually impose the embedment depth. Just check the box and enter the user-defined value, for instance 350 mm. The combined load has dropped to 76%. You can now print the calculation results. However, before we do that, let's navigate to the Project Details tab and enter data characterizing the given project to be included in the printout. For instance, the project name and subject. In the Documents tab, you can extract technical data from the relevant library of technical approvals, data sheets, or .dwg drawings. This can also be done later on. Let's proceed to the printing and click the right icon. The program reminds you of the unfilled data fields in the Project Details tab. You may obviously proceed if you don't mind the missing details. You are now offered the opportunity to select or change the print language. Once your choice has been confirmed, a .pdf document starts being created. The printout contains a table at the top section showing the information entered in the Project Details tab. Other data you will find in the printout include the anchor type, the effective embedment depth, the substrate type, the predefined base plate, and the section. In other words, all the details entered in the data tabs. There is also a picture of the model with the neutral axis marked and the predefined load values, resultant forces acting on individual anchors, and calculation results collated in the table, including the total combined load, which equals 76% in the case analysed. This means the connection is correct. The last page contains installation data and an installation drawing. Thank you for your attention. I strongly encourage you to use the EasyFix program.